Okay, we're at the very, very last topic. Finite difference methods for two-point boundary value problems. After covering linear problems last time, today I'll talk about nonlinear problems. So, as a quick refresh, this is the boundary value problem that we're solving. Y double prime is a function of x, y, and y prime on this interval AB, and the solution must satisfy these two boundary conditions. Now, the general form of a finite difference method that we're working with is where we solve a system of equations. Um, this system right here. So we have a system of n equations. So n is the number of interior grid points, and um, we're solving for y values, y1, y2 up to yn. So each yi is a value of is an approximation to y of xi, where xi is one of the interior points in the interval AB. So those are our n unknowns, and these are our n equations that they must satisfy. Now, in a case, as I mentioned last time, where I is equal to 1 or n, so the points that are closest to the boundary, then we need to fill in where we have wherever you see y 0, um, it will be alpha, and whenever it's y n plus 1, that would be beta. And I just realized there's a typo on this line. And I should make sure that it's not also a typo in the book. Um, oh, yes. It is a typo in the book. I need to fix it here also. So right here, there should be yi plus 1 minus yi minus 1. So let me correct that real quick. So you see it's this rule up here. This rule is correct, but mistake was made here. I apologize. I need to quickly look through some other notes. Oh, so the irony here is that in the book, this is wrong and this is correct. In these notes, it's vice versa. So at least here in these notes, I need to make both of them correct. Okay, so that would be yi minus 1 for the centered difference. Okay, so here are equations with the boundary values taken into account for first and last equations. Now, last time, filling in the form of f for a linear ODE, we wound up with a system of linear equations. So basically solving an ax equals b, or in the notation of last time, an ay equals r problem. Not anymore. Now we have a system of nonlinear equations to solve, so we must use iterative method, like one of these root finding methods that were talked about previously, such as Newton's method, or generalization of a secant method, or fixed point iteration. Today I will focus on Newton's method. So what I will do is write out the system for the nonlinear case, and then discuss how Newton's method can be used to solve it. So I'll carefully scroll here. Okay. So we solve the system of nonlinear equations f of y equal 0. I have everything in bold here because everything in this equation is a vector valued quantity. So y is a vector of our unknowns, y1 to yn, our solution at our grid equally spaced grid points, interior points. F is a vector valued function of y, characterizing the spatially discretized ODE. And here we have a 0 vector. So we have this n vector must be equal to 0, where f has component functions. Okay, so the component functions of f are f1 of y, f2 of y, and so forth. All the way to fn of y. So each one of these is a function of the vector y, but it returns a scalar value, and together they all make a vector. And I'm going to put a transpose here because by convention we have vectors being column vectors, but I've written this out as a row. Now, what are these component functions of capital of f? Okay, so we have f1 of y. So this will return a scalar value based on the components of a vector y. So what we'll have is, and this is in keeping with the system of equations I showed you earlier, I'm just writing it out a little more concretely. So we have the center difference for the second derivative, and because this is the first equation, y1 is our first interior grid point. We use points to the right and the left. But to the left is the boundary point, x equals a, and at that point the solution is equal to alpha. So this is, you can think of this as y0, but we know what that is for the boundary conditions. Minus f evaluated at x1, y1, and then we're approximating y1 prime by also a centered difference. Okay. So that's our first equation. Then for the equations 2 through n minus 1, so all of our equations except the last, we can specify in one shot. So yi plus 1 minus 2 yi plus yi minus 1 all over h squared. That's the center difference for second derivative minus f xi yi, and then the center difference for the first derivative. Make sure I get that in right this time. Okay. All right, something's off here. Xi, yi, okay, my center difference. Okay, that part is fine. Alright, I'm not sure what's going wrong here. I'll have to... Oh, I see what happened. I forgot to mark this as a left parenthesis. Okay. Alright, and then, because now these equations do not deal with the boundary conditions because they're too far interior. Then for the last equation, f, okay, so I'll make a note that this last equation applies for I equal 2 up to n minus 1. And then finally, the last equation, which needs to take into account the boundary condition on the right. So that would be yn plus 1, which would be beta from the second boundary condition, minus 2yn plus yn minus 1 minus f n yn, and then the second center difference for the first derivative. All right, so I have beta minus yn minus 1 all over 2h. Okay, so these are the n equations in the n unknowns, y1, y2, up to yn, that we need to solve using some uh, root finding method. Okay, so I'm going to recap um, Newton's method, originally covered in section 10.4 for a system of equations, and that was covered in section 11.1. So the main iterative step for Newton's method is xk plus 1. Actually, I'm going to use y in this case because that is our solution. Is equal to yk. You may recall Newton's method for a single equation, we'd subtract off, so it'd be yk minus f of yk over f prime of yk. But here we have a system of equations, so instead I'm going to indicate by sk whatever has to be added on to yk to get yk plus 1. And then I will define that, where the Jacobian of f evaluated at yk is defined to be minus, I need to include sk here. Sk, so Jacobian times sk is equal to minus f evaluated at yk. All right, so to explain this, and this is a review, but still, how would I get sk? I would multiply both sides by the inverse of this Jacobian matrix JF. So sk is equal to minus the f value, and I say loosely speaking, divided by the derivative, but really we're multiplying by the inverse of a derivative, which is a matrix. But you can see how it fits the general form of Newton's method. So we have f specified. It's these functions right here. So we can evaluate that at whatever y we have, beginning with our initial guess. But what we also need is this Jacobian matrix. So how can that be specified? So to get the Jacobian matrix, JF, evaluated at any given y, how do you do this? You need to take partial derivatives of each fi with respect to each yj. So remember, this is a matrix, so we have to define the ij entry, and that's how you get it. Partial derivative of fi with respect to yj is the ij entry of this matrix. But notice that each one of these component functions of f depends only on, at most, 3 y values. So fi depends on yi minus 1, unless it's a boundary point, and yi plus 1, unless it's at a boundary point. When the indices match, that's a diagonal entry. So the derivative of fi with respect to yi gives me the ii entry, so that sits on the diagonal. And with a dependence on yi minus 1 and yi plus 1 and no other y values, this Jacobian matrix is actually tridiagonal. So to show you the derivatives, I will carry out the differentiation for you. Okay. Now, first for the diagonal entries. So the Jacobian of f at y, the ii entry. I'm going to take the derivative of this with respect to um, with respect to yi. So yi plus 1 and I minus 1, yi plus 1 and yi minus 1 are independent variables. So derivatives of these with respect to yi would be 0. So all I'm going to get from this part is minus 2 over h squared. So whatever's multiplying yi here is the only thing that survives. Then over here, I have derivative of this with respect to yi, but yi does not play a role in this center difference. We only have it here. So by the chain rule, I need a derivative of f with respect to y evaluated at um, uh, these same points, xi, yi, and then the center difference for first derivative. Now I want to point out, since there's a typo in the book about this, so this is the same thing as the partial derivative of fi with respect to yi evaluated at whatever y we have. I mention this because in the book, this f is lowercase, it's supposed to be uppercase. So it's correct here, it's a typo in the book. Okay. Now, okay. And this holds for all diagonal entries, 1 to n. Now, next, I want to look at derivative with respect to yi plus 1. So this is the entry in row I, column I plus 1. All right, so that would be partial of fi with respect to yi plus 1. Okay. So now if I look at this expression here and differentiate with respect to yi plus 1, this is the only part from the center derivative approximation to deal with. So that would be 1 over h squared. And then I move on to this term right here. And the only dependence on yi plus 1 is here in the center difference for first derivative. And that's with the y prime argument. So I need partial of f with respect to y prime evaluated at these same points. So I can just go ahead and copy those. But then look at what's done to yi plus 1 here. It's multiplied by 1 over 2h. So by the chain rule, I need to include that as a factor. Whereas here we just have yi by itself, so I didn't need to multiply by anything. And this holds for I equal 1 up to n minus 1. And the reason why is when I is equal to n, that's here, yn plus 1 is beta. It's a fixed value, a constant. So we're not taking a derivative with respect to it. And we're in the last row. There is no super diagonal entry anyway. So this is the super diagonal where the row index is less than the column. And finally, for the subdiagonal, so I minus 1, okay, it's going to be very similar to this. So I'm just going to copy and adjust. Okay. So it's a derivative with respect to yi minus 1. And if we look here, derivative with respect to yi minus 1, again, is multiplied by 1 over h squared, so this term does not change. And then we have over here, here yi minus 1 is multiplied by minus 1 over 2h. So that's going to change this sign to a plus. And that's the end of that formula. We just have to be careful about our indexing. It starts from 2 up to n, where we index I minus 1 would actually make sense to refer to a variable. So here's how we fill in the Jacobian entries of the entries of a Jacobian matrix, which turns out to be tridiagonal. Okay. Now these formulas, we rely on this notation for boundary points. So y naught, wherever that appears, is alpha, y n plus 1 is equal to beta. Also, as I mentioned, Jacobian is tridiagonal. So at least the system is easy to solve. One of the knocks against Newton's method, justifiably so, is that you're solving a system of equations at every iteration. If you have n equations, normally you're incurring n cubed flops to solve that system of equations with whatever Jacobian you have. But in this case, the Jacobian is sparse. It's a and banded. It's a tridiagonal matrix. So solving this system is quite efficient. Okay. So so now we know how to set up this system, and I can go ahead and solve it at each iteration. The only thing that's missing initial guess. Now, there are many things that we can do, but a simple choice. Okay, so y0 is equal to alpha plus I'm actually using point slope form here. So we take our vector of equally spaced x values, x here, and subtract a and then multiply by beta minus alpha over b minus a. So in other words, if x is equal to a, all of this would go away. We'd have alpha, as we should for the left boundary. If x was equal to b, we'd have b minus a over b minus a canceling. Then I'd have alpha plus beta minus alpha. Alpha's canceling, and I'd have beta. So the linear function in x that satisfies the boundary conditions. So we could always use that. We should use something that satisfies the boundary conditions at any rate. Okay, so so now what I'll do is step through an example real quick. Okay, somewhere I have the boundary value problem. So y double prime is equal to y cubed minus y prime. So its right side is our f of x, y prime on the interval 1 to 2. The boundary conditions, y1 equals 1/2. Y of 2 on the right boundary is 1/3. Okay. So then we have is f x y prime is equal to y cubed minus y prime, and we need partial derivatives. The f dy is equal to, so I take a derivative of this with respect to y, treating y and y prime as independent variables. So I'd have 3y squared minus y prime. And then derivative of f with respect to y prime. Well, the derivative of this with respect to y prime would be 0. I'd only have this term making a contribution. That contribution would be minus y. So our system of equations to solve is the following. Okay, so it has a form f of y equals 0. So the component functions in this case would be, so f1 of y would be equal to the approximation for the second derivative, center difference, so y2 minus 2y1 plus the left boundary value, y0, which is 1/2, all over h squared, minus, and then we have our function f, so that would be y1 cubed, so I'm referring to this, so minus y1 times y1 prime, which is equal to y2 minus y0, which is 1/2, all over 2h. Okay. Now, so that's the first equation. And then the interior equations would be y plus 1 minus 2yi plus yi minus 1 all over h squared. And then we fill in the function f, again using the center difference for the first derivative. Okay, and this holds for interior indices. And last equation, all right, so then yn plus 1, but that's the right boundary value, so that's 1/3, minus 2yn plus yn minus 1, minus the valuation of f at the last interior point. So that would be yn cubed minus yn. So now I have yn plus 1, but that would be, oh, I just realized this should be a uppercase n. So I'd have the right boundary value, which would be 1/3, minus yn minus 1 for the center difference. Okay, so this defines a system of equations to solve, but now we also need the Jacobian matrix. So using the formulas from before, okay. So for the diagonal entries, notice I need df dy, and I have that down here. It's 3y squared minus y prime. Whereas df dy prime is just going to be minus y. Okay, so I can also think of it in terms of differentiating these formulas with respect to y and y prime, if you will. Well, not so much differentiating with respect to, well, actually, yes, I can do it that way. So if I take Jacobian matrix diagonal entry, so differentiating fi with respect to yi, so that's going to be, well, there's multiplying yi, so minus 2 over h squared, that's a constant factor, okay, and then minus, I need to take a derivative of this with respect to yi, so that's going to be 3 yi squared minus, now yi plus 1 and yi minus 1 are independent variables of yi, so this whole standard difference is treated as a constant, so I'm just going to subtract that off. And that's that for the diagonal entry. And then the super diagonal entry, um, okay. If I take a derivative of this with respect to yi plus 1, so if I did 1 over h squared, the constant that's multiplying yi plus 1. And then over here, I don't get any contribution from this. So it's whatever's multiplying yi plus 1. Well, that's minus yi over 2h, and then we have another minus, so that would give me a plus yi over 2h. And then finally, the subdiagonal entry, first part's going to turn out the same way. So there was multiplying yi minus 1. It's 1 over h squared. And then here, whatever's, I look at the term involving yi minus 1. Well, that's multiplied by minus, minus, minus. So minus yi over 2h. And so here we have the entries of the tridiagonal Jacobian matrix. Okay. Now, so the last thing I want to mention is, okay, an example 13.2.3 for code to set up a boundary value problem. So it's actually, let's see, let me get my pages in order here. Actually, it doesn't do that. For code to evaluate f of y. Okay, need to go to the next page here. So similar code to evaluate the Jacobian matrix. Is one of the homework problems, but the idea is it works fairly similarly. Okay. And the other thing I want to mention is code from example 13.1.3. Let me make sure I have that right. Yes. That calls a shooting method function can be used here by calling a function to solve by finite difference with Newton's method instead. Um, so one of the problems on the coding option for final is to um, uh, do that. Actually, I want to check um, real quick which problems from this section I actually assigned, because some I chose not to save them for the coding option for final. For those of you who want to do that, so the problems I assigned are 1, 5, and 6. Um, okay. Okay. So um, I'm looking at those problems. So it's not in the homework. Um, I did not give any homework problems for 13.2 that involve MATLAB. I saved those problems for a final, for those of you who want to do that. Okay. Um, but the code in this example is very generic. It sets up a BVP and then calls whatever function you want to use to solve it with the needed parameters like information about the boundary conditions, information about the function little f, and its derivatives if needed for Newton's method, and so on. Okay. All right. Now the other thing um, worth mentioning is that okay. Here we've talked about only using Newton's method. Can use other root finding methods for systems. And those when I say for systems, that means like not bisection. Bisection method is good for one-dimensional problems. Doesn't generalize in any meaningful way towards solving systems of equations. But other methods like fixed point iteration, Newton's method, secant method do have generalizations. Um, so like fixed point iteration or secant method. An advantage of doing so, but you don't need to work with partial derivatives of f, like Newton's method does. Um, so Newton's method has that one key disadvantage that it requires derivatives of a function you're trying to find a root of. So that means specifying its derivative in some way, that means partial derivatives of little f with respect to y prime. So secant these other methods, all you're doing is evaluating a function capital F at whatever y values, and you don't need this derivative information. Okay, so um, that's the make sure there's nothing important here, but I'm leaving out. Okay. Actually, while on the subject of um, other iterative methods, you can prove that fixed point iteration will converge if h is sufficiently small. And can't type. And C exploration is not a problem that I assigned, but the details for 13.2.7 details on what assumptions need to be satisfied to guarantee convergence and how a fixed point iteration um, is set up. Um, so, um, and what's assigned in that problem is to prove that fixed point iteration will converge. So I was trying to be merciful and not assign that, but it is something of interest that it is possible to guarantee convergence in such cases. Because Newton's method, you had to be careful about choosing your initial guess that the iteration might fail otherwise. Okay, so that's the end of the material. I've heard from one of you about what you want to do for the final. Rest of you, please let me know. Please try to keep the homework coming in. I will be catching up on grading very soon on what's been turned in, but that hasn't been very much. So, um, best of luck to you with what remains in this class and also your other classes.